Hi everyone. Today I wanted to discuss finding inverses. So we'll take a look at two instances of finding the inverse algebraically and then take a look at an inverse application as well. So our first step is rewriting f of x as y. So we're going to interchange the variables here. So where there's a y, we're going to replace it with x. Where there's an x, we'll replace with y. And now we want to solve for y. So our first step is going to be to add the 9 and divide by 2. And now we want to think about what is going to undo a power of 7. So that is going to be the 7th root. So we're going to take the 7th root of both sides, or if you want to think about it as taking both sides to the 1/7 power, that also works. And again, the point of that is that the 7th root and the 7th power are going to cancel, just leaving us with y plus 3 on the right. Our last step will be to subtract 3 and rewrite it in inverse notation. So the inverse of our original function f is the 7th root of x plus 9 divided by 2 minus 3. Now let's take a look at g of x. Again, our first step is going to be to interchange our x and y variables. And again, we're looking to solve for y. So what we know about solving log equations is that we want to isolate the log part. So we'll go ahead and start by subtracting 4 and dividing by 5. And we'll be left with x minus 4 divided by 5 equal to the log of 2y. So we know this log has a base of 10. It helps some people to go ahead and write that in there. And to use our definition of log, it helps a lot of people to rewrite this with the log on the left side as well. So I'm going to go ahead and do that here. And now we're ready to use our definition of log to turn this into an exponential statement. This is going to read 10 to the power of x minus 4 divided by 5 is equal to 2y. Dividing by 2 and rewriting in inverse form will give us our final answer here. And that will read g inverse of x is equal to 10 to the power of x minus 4 over 5 divided by 2. And now we're going to take a look at an application of inverse functions. So what we're told is that in 2007, the Richmond Zoo had 24 albino alligators, and they increase about 5.7% each year. So we're going to find an equation to model this situation. We are going to call it A of t. This is going to be an exponential equation because we have a percent increase each year. We know our exponential equations have the form y equals a times b to the x. So our a is going to be our initial value, that's going to be 24. And our b, the base of our exponential function, comes from the percent change we have. So adding 1, which represents 100%, plus the 0.057, the 5.7% increase we have each year, we are going to get a base of 1.057. Since our initial value of 24 was from the year 2007, if we want to figure out how many albino alligators we should have in 2012, we're going to let t be equal to 5. This is 5 years from what we called our starting point. We get an answer of about 31.7, but 0.7 of an alligator is a little gross, so we'll call that about 32 albino alligators. To explain why this function is invertible, in other words, how we know it has an inverse, what we need to remember is that functions have to be 1-to-1 to have an inverse. So in addition to every x value corresponding to only one y value, that's our function definition, every y value has to correspond to only one x value. And we can use the horizontal line test to test that out. So if we were to graph our exponential function, it would look something like this. And what we can see is that any horizontal line we draw is going to intersect our graph at most 1. And so we know it's invertible because it is a 1-to-1 function because it passes the horizontal line test. Now we want to find the inverse of this function. And for our application problems, I think it's easier if we do not change our variables because that helps us with the interpretation. So we're going to go ahead and solve for t. Our first step is going to be dividing by 24. In order to solve for the exponent, we need to use logs. We have a couple ways of doing this. We can take log base 1.057 of both sides. We can take the natural log of both sides or the common log of both sides. A lot of people like the common log, so we'll go ahead and take the log of both sides here. And remember what that allows us to do. We have a property of logs that says if we have an exponent within a log, we can bring it down front and make it a product. And that allows us to solve for t. So we'll go ahead and divide by the log of 1.057, and we will have our inverse function. You may not think it looks pretty, but here's what our inverse function looks like if we choose to take the log of both sides. If we want to determine what our inverse function represents in this situation, let's think about our original function. In our original function, we input a year, and the output was our number of albino alligators. Our inverse is going to do the opposite. So if we know the number of albino alligators, we can figure out in which year that happened. So lastly, if we want to find and interpret a inverse of 100, we are going to use our inverse function. We are going to input 100 into the independent variable, which in this case is a. So remember, with our inverse function, the input is the number of alligators. So we're going to have 100 albino alligators 25.7 years after 2007. In other words, in 2032. I hope you have found this helpful.